Hi everyone, this screencast is going to take a look at the Kinetics practice test. In each of these questions, I'm hoping to highlight some key misunderstandings and key ideas because remember, it's more important that you understand the underlying concepts behind each question. You can't possibly just memorize answers because each question is always slightly different. In question 1, we're focusing on collision theory. So collision theory has a couple parts. The first part is kind of understanding that in order for a reaction to occur, you have to have a successful collision, and that successful collision has to have particles in the correct orientation and with enough energy. And when successful collisions happen, you make a product. There are many factors that can lead to more successful collisions and more collisions overall. And this is what this question is really addressing. So, nature of reactants, concentration, temperature, surface area, adding catalysts, those were all things that we could potentially change about a reactant in order to get the rate of the reaction to go faster. Remember to pay attention to phase because you can only change the surface area of a solid. You can't change the surface area of a gas. And the other most important thing is that the substance that you change has to be in the rate law. Even if it's a reactant, that reactant might be zero order. It might not be in the rate law, so those changes won't impact the overall rate. Question 2 has us looking at a graph of volume of carbon dioxide over time, where 3 different trials were done using various concentrations of hydrochloric acid as they react with calcium carbonate. The gas being produced is carbon dioxide. In part A, the most concentrated acid, 3 molar, would result in the rate of the reaction happening the fastest. So we can see from the slope of the line, which is indicating rate, the change in volume of concentration over change in time. The slope is the steepest for trial A, and that's going to result in the 3 molar acid being used. Now, over time, for all of these graphs and all of these lines, the rate decreases. And this is simply because as the reaction is proceeding, the concentration of your reactant, HCl, is going down. Think about this in terms of an ice diagram. The reactant side, the change line, it's a negative. Your concentration of reactant goes down as it gets consumed. You're making more product. You're diluting your acid. Therefore, the rate is going to vary. Remember, when changes in concentration affect rate, that means that the order is first order or second order. And for part C, we end up all producing the same volume because of stoichiometry, just the concentration of the reactants, the mass of the calcium carbonate. Since various concentrations were produced and we produced the same volume, it must have been the calcium carbonate that was limiting because it didn't matter that that we started with different concentration of acid. We had the same final product. So that's another little tidbit for there. Number 3, give the letter of each of the following statements that are true. Most reactions occur at a constant rate. That's not true. Typically, changes in concentration impact rate. Most reactions are first and second order. B, the rate of the reaction can only be measured in terms of amount of product produced and not the amount of reactant. That's false. We can measure anything in the reaction as long as we're measuring something that's changing about the reactant or product and time. And C, this is a big one, you cannot determine the rate law from a balanced equation. That is just not right. You always have to determine the rate law experimentally. Number 4 ties to energy profiles or potential energy diagrams. Remember, the sign of delta H indicates whether the energy has been absorbed or is released. So delta H positive is endothermic and delta H negative is exothermic. Question 5. When the concentration of the reactants are increased, the rate of the reaction increases. How is this best explained using collision theory? So remember, the various parts of collision theory that we have to consider are the number of collisions, the fraction of collisions that are colliding at the correct orientation, and the only thing that will change that is a catalyst, and the fraction of collisions with sufficient energy. The only thing that can change that is temperature. So we're just talking about the fraction of collisions with that have a certain frequency. We're increasing the number of collisions when we increase concentration. Question 6 is the same idea as question 5, but now we're talking about temperature. So here we have that idea that we are increasing the energy behind each collision. So more of the collisions are going to have that sufficient energy requirement. And we're overall increasing the collision frequency because remember, when we increase temperature, we increase the kinetic energy of the particles. They're going to be colliding more often and they're going to be colliding with more energy. Now, number 7, you can actually solve a couple different ways. When you look at the question, you're told that it's zero order. So what you might want to do is jump to the zero order integrated rate law, which would be fine. You can plug in the values, you can solve for K, no problem, easy. The other thing that we need to remember is when a reaction is zero order, changes in concentration don't impact rate. So as long as we remember that rate is the change in concentration over the change in time, and since the rate is going to be constant because it's zero order, we're essentially just going back to a very simplistic change in concentration over change in time formula. They are essentially the same thing. The only thing that the zero order integrated rate law reminds you is that the K, the rate constant, is the rate in this case. Remember, when zero order reactions are present, the rate is equal to K. For 8 through 10, you're reading and interpreting a graph. This graph shows that the rate is not constant because it's a curve. So the main thing to remember is if you wanted to calculate the rate, you have to find the slope. And that's essentially what we're doing in number 8. We're calculating the slope using the point slope formula. In number 9, this is a reminder of how instantaneous rate is determined. This also appears, as I have in this note, number 5 in your open response. So you would not be actually asked to calculate this, but you should know how to do it. Number 10, visually inspecting the graph, we're looking for the steepest part of the graph. The steepest part is at the 10-second mark. Therefore, that's when the rate has to be the fastest. Number 11. This goes back to something that we talked about earlier. When you look at a balanced equation, you cannot predict the rate law from the balanced equation alone. You need some kind of experimental evidence, and that experimental evidence could be a mechanism or like a data table or a graph in order to get the reactants orders, but it has to be evidence. Now here we have a balanced equation and a rate law provided. The order for hydrogen is first. Again, we're identifying that based upon the rate law. The overall order is third. And then 14 asks, what happened if you would double the concentration of NO, but the concentration of hydrogen stays the same? So I did a little problem, a little 2 squared, to remind us that that would equal 4, and the rate would quadruple. Question 15 is our classic stoichiometry using rate. So the big thing to remember here is as long as there hasn't been a time change, it's at the same time, or if it was talking about the initial rate, you can use just regular stoichiometry. If there ever is a time change involved, that's where you have to use the method of initial rates. That's where you have to use potentially an integrated rate law, and you may need to think about using an ice diagram. If time has passed, to keep track of that stoichiometry, remember in the ice diagram, it's the change line and the mole ratio that together will help you figure out a concentration of something else. All right, here's another question, 16, that's kind of asking you to figure out what the rate law might be from some information. If we triple the concentration of chlorine gas, the rate increases by a factor of 3. So right here, that kind of tells me that chlorine is going to be first order. When we triple the concentration of both reactants, the rate goes up by a factor of 27. So I created a little algebra expression here. We know this is 3 to the first, which is 3. We know this is 3 to the we don't know. And we know the product of those two has to be 27. So that means this has to be a 9, which means the order has to be second. So not too tricky, but don't be afraid to write it out. Don't be afraid to leave yourself a couple notes about what the information in the question is telling you. Number 18, this is the method of initial rates, where we're going to use the data in the table to write the rate law first. And then once we have a rate law written, we can always solve for the rate constant, which is part B. So again, when we look at the data here, we have to compare trial 1 to trial 2. The chlorine doubles in concentration and the rate doubles. So that means the chlorine must be first order. If we wanted to compare for the NO, trial 3 and trial 4, when the initial concentration doubles here, we're getting our rate to go up by 4, so this is second order. Notice here all the exponents are the same, so you can just compare the number out front. All right, this next section is all about this mechanism. So in a mechanism, you should be able to identify catalysts, intermediates, write the overall balanced equation, which we can see in number 19, identify molecularity. Remember, unimolecular means there's one particle. Bimolecular means 2 particles. If there were 3 particles, that would be termolecular. 21 has us identifying the catalysts and intermediates. 22, evaluating whether changing the concentration of a reactant would impact the overall rate. So we can see that the 2 reactants are the C4H9Br and the water. However, when we look at our mechanism, the water is in the fast step, so that would not impact the overall rate. Only changing the concentration of a reactant in the slow step will change the rate. And then lastly, an important skill with mechanisms is writing the rate law from the mechanism. When the slow step is first, just use the rate law for the first elementary step as the overall rate law. which is choice C. '24, identifying catalysts, which is another key component of reaction mechanisms. All right, these next few questions are going to focus on potential energy diagrams. Remember, the key idea from potential energy diagram would be activation energy, transition state, activated complex, and how a catalyst impacts the activation energy. 25 is just very straightforward, basic identification of the parts of the diagram. 26, calculating the enthalpy or the heat of the reaction. We'll spend the entire next unit focused on this, so I'm not going to be asking you to do a calculation like 26 on the test. 27 is important because we can clearly see that when the catalyst is added by the dashed line, that the activation energy is lower. Pay close attention though. This does not change the potential energy of reactants or products. This does not change the enthalpy of the reaction. It just impacts the activation energy. And finally, on 28, we're looking at kind of explaining using collision theory. So be careful for questions like this. Think back to our gas laws unit when we had to explain the behavior of a gas according to kinetic molecular theory. You have to make sure that you're explaining the explicit part of the theory that's being impacted by this particular change. So when we add a catalyst, this decreases the activation energy. This means less energy is required to meet the activated complex. Therefore, more particles in the sample have reached that minimum energy that's needed, and therefore the percentage of effective collisions has gone up. So in collision theory, we're looking at general, does the number of collisions overall change? Do we impact the effectiveness of the collisions? And third, do we impact the orientation of the collisions? Catalysts also can play around with that orientation piece, but when we're talking about a potential energy diagram, the focus there is on that activation energy. '29, one more question here about energy profiles. Remember, we can predict relative rate by looking at the activation energy on an energy profile. If a particular energy profile shows a large activation energy, that says that the reaction rate is probably going to be pretty slow compared to an energy profile that shows a small activation energy. If you remember on one of our worksheets, we looked at the energy profile for the mechanism where we had those two kind of humps, those two hills. And one of the questions was to compare, does this energy profile match the mechanism? In that situation, you were looking for the sequence of the fast step versus the slow step. And if the activation energies in the profile aligned with being fast or being slow. All right, the next 30 and 31 are really focusing more on your understanding of rate law and your understanding of the rate constant. So again, if we look at 30, oxygen is a reactant. We're trying to double the concentration of oxygen. However, oxygen is not in the rate law. So it's not going to impact the rate, and nothing other than changes in temperature are going to impact the value of K. For 31, this is looking at the overall order, which is third order, and your ability to come up with units on the rate constant. I do apologize that there was an error on your original practice test. The answer choices for C and D were both incorrect. I have made the modifications to that here, but one of the things to remember as a little bit of a shortcut is when your overall order is given and you know the overall order, the exponent on molarity will be 1 less than the overall order. Now remember, molarity is always a negative exponent and time is always the negative exponent, but that can be a simple way for you to identify the units based upon the overall order. All right, so 32, we're looking at kind of an integrated rate law question where we're looking at graphs of changes in concentration over time and using the graph to identify the particular order of a reactant. Which graphs indicates the changes in the concentration of dinitrogen oxide over time? Well, it says that it's second order. So the linear graph would have to be 1 over concentration versus time, which is graph C. If we had graph C and we were trying to figure out the rate constant, or K, we would just use the slope of the line. The line is positive, so we don't have to worry about taking the negative slope. Just read the slope of the line, and that will be the value of K. 33 is half-life. So feel free to kind of jot down a little table that might show how half-life is going to change. We know the half-life of uranium is 12 days. If we started with a sample of 8 grams, how much of the sample will be radioactive after 30 days? Now you kind of have to be careful because 30 days is going to be in between half-lives, because we're going to have 12 days is the first half-life, 24 days is the second half-life, and then by the time we get to that 36th day, we're going to have undergone 3 half-lives, but we're right in between. So this is where you have to be thinking 8 grams gets cut to 4 grams, gets cut to 2 grams, gets cut to 1 gram. You're in between 2 and 1. So that means you're somewhere. The only choice that's going to be there is the 1.44. So this is definitely one that you might want to diagram out if you get stuck. If I think about it after this video, I'll go back and I'll make a couple notes. 34, again, what factors will impact the rate constant? And this question is asking about activation energy. We do know that the rate constant is impacted by temperature. If the rate constant goes up, the rate constant will go up if the temperature is increased, but activation energy does not change. So remember, activation energy is kind of a arbitrary value that's been defined for a reaction. On our Maxwell-Boltzmann diagram, we draw that vertical line that says this is the minimum amount of energy needed for that reaction to react. And when we change the temperature by maybe introducing a second curve onto our Maxwell-Boltzmann diagram, we don't change where the line is. The line is exactly where it was before. The only difference is because we've created a separate, different curve representing that different temperature, we have a different number of particles that have made it past that activation energy line, but that line is exactly the same. Which statement is correct about the rate law for a chemical reaction? It can be determined from the balance equation. No, we've already seen that. It can be used to predict the change in heat. Change in heat is enthalpy. Nope, can't do that. It will include every reactant, since changing the concentration of any reactant will impact the rate. No, because it could be 0 order. It would be in the fast step of the mechanism. Or it can be determined by measuring changes in concentration of a reactant or product over time. Yes. 36, writing rate law from a mechanism. We've seen this before. Slow step is first. This is the easy way to do that. Just use the rate law for the first elementary step. 37, a little bit more with mechanisms. Now be careful, because even I today, when we were going over the formative, made an error when I was looking at the question. I wasn't reading it carefully. I want the rate law for the second elementary step, which is this one. So it's just going to be the X and the NO. Here I want the rate law for the overall reaction. So I'm going to have to go back to the second elementary step, substitute out the X and put in place the H2 and the NO, because this is a intermediate. Intermediates are not in the rate law. And I'm going to end up with choice C. Why is it that some collisions between reactant molecules do not form products? Because they don't have the right amount of energy. Again, going back to collision theory, it's energy and appropriate orientation. We talked briefly in class about this. I wouldn't focus a lot of time on it because I'm not going to ask you about this specifically on this exam. But the key understanding is homogeneous means the same, uniform, heterogeneous, not the same. So in order to be classified as a homogeneous catalyst, you have to be in the same phase as all of your reaction. So since everything here is a gas and this is a gas, this would be called homogeneous. In all the other situations where you have a solid catalyst, sometimes they call these a surface catalyst, they would be a heterogeneous catalyst because it's in a different phase than what your reaction is in. All right, here's that energy profile for a two-step mechanism that I was talking about earlier. We can tell from this that the first step has a much greater activation energy than the second. So the first step is going to be your slow step, and the second step is going to be your fast step. All right, in this next mechanism, they have not identified the fast or the slow step, but they're giving you some information about how changes in concentration impact the rate. So they're kind of getting you to know that the rate law should be this. According to this, the rate law has to be some rate law where the H2O2 is first order, based upon knowing that if you double the concentration of H2O2, you double the rate. So you just have to work out, well, if that's the case, which step has to be slow to get my hydrogen peroxide to be first order? And the answer there is the first step. Because if it wasn't the first step, the H2O2 would be second order, and that wouldn't work. 43, Maxwell-Boltzmann. You definitely should be able to draw a Maxwell-Boltzmann diagram and use that diagram to explain how a catalyst changes the activation energy, or how a different temperature changes the number of effective collisions. It's something we've done before, but now we're kind of applying it to this new situation. So remember, the catalyst lowers the activation energy. So as we can see from the shaded area, we have more particles that are meeting that minimum energy needed to react. All right, I'm going to take a pause here, and I'm going to pick up with a second screencast that covers the open response. So I'll be back.